Hello and welcome. In this video, we'll be going through a brief overview of the structure and capabilities of the TensorFlow library. So let's get started. TensorFlow is an open source library developed by the Google Brain team. It's an extremely versatile library originally created for tasks that require heavy numerical computations. For this reason, TensorFlow was geared towards the problem of machine learning and deep neural networks. Due to a C++ back-end, TensorFlow is able to run faster than pure Python code. The last thing I'd like to mention is that a TensorFlow application uses a structure known as a data flow graph, which is very useful to build and then execute it in a session. It is also a very common programming model for parallel computing. We'll cover this in more detail shortly. TensorFlow offers several advantages for an application. For instance, it provides both a Python and a C++ API. It should be noted, though, that Python API is more complete and is generally easier to use. TensorFlow also has great compilation times in comparison to the alternative deep learning libraries, and it supports CPUs, GPUs, and even distributed processing in a cluster. It is a very important feature as you can train a neural network using CPU and multiple GPUs, which makes the models very efficient on large-scale systems. TensorFlow's structure is based on the execution of a data flow graph. So, let's take a closer look at this. A data flow graph has two basic units: the nodes, that represent a mathematical operation, and the edges, which represent the multidimensional arrays known as tensors. So, this high-level abstraction reveals how the data flows between operations. Please notice that using the data flow graph, we can easily visualize different parts of the graph, which is not an option while using other Python libraries such as NumPy or scikit. The standard usage is to build a graph first and then execute it in a session. So, what is a tensor? Well, as we've already noted, the data that's passed between the operations are tensors. In effect, a tensor is a multidimensional array. It can be zero-dimensional, such as scalar values, one-dimensional, as a line or vector, or two-dimensional, such as a matrix, and so on. The tensor structure helps us by giving us the freedom to shape the dataset the way we want. It's also particularly helpful when dealing with images, due to the nature of how the information within images is encoded. Indeed, when you think about an image, it's easy to understand that it has height and width. So, it would make sense to represent the information contained in it with a two-dimensional structure, such as a matrix, for example. But, as you know, images have colors, and to add information about the colors, we need another dimension, and that's when a three-dimensional tensor becomes particularly helpful. Now, let's take a look at a data flow graph and see how tensors and operations build the graph. As mentioned before, in a data flow graph, the nodes are called operations, which represent units of computation. The edges are tensors, which represent the data consumed or produced by an operation. In this graph, feature matrix is a placeholder. Placeholders can be seen as holes in your model, holes through which you can pass the data from outside of the graph. Placeholders allow us to create our operations in the graph without needing the data. When we want to execute the graph, we have to feed placeholders with our input data. This is why we need to initialize placeholders before using them. Let's look at another operation which builds the variables for our program. In this graph, weight matrix is a variable. TensorFlow variables are used to share and persist some values that are manipulated by the program. Please notice that when you define a placeholder or variable, TensorFlow adds an operation to your graph. In our graph, weight matrix and feature matrix should be multiplied using a multiplication operation. After that, add operation is called, which adds the result of the previous operation with bias term. The output of each operation is a tensor. The resulting tensors of each operation crosses the next one until the end where it's possible to get the desired result. After adding all these operations in a graph, we can create a session to run the graph and perform the computations. For a better understanding of TensorFlow graphs, I recommend that you run the labs from this module, which walk you through different elements of the data flow in the TensorFlow library. As previously mentioned, TensorFlow comes with an easy-to-use Python interface to build and execute your computational graphs. But what makes TensorFlow so popular today is its architecture. TensorFlow's flexible architecture allows you to deploy computation on one or more CPUs or GPUs, or on a desktop, server, or even a mobile device. This means you build your program once, and then you can run it easily on different devices. So, let's briefly review the reasons why TensorFlow is well suited for deep learning applications. First, TensorFlow has built-in support for deep learning and neural networks, so it's easy to assemble a net, assign parameters, and run the training process. Second, it also has a collection of simple, trainable mathematical functions that are useful for neural networks. Finally, deep learning as a gradient-based machine learning algorithm will benefit from TensorFlow's auto-differentiation and optimizers. This concludes the video. Thanks for watching.